In this video, we're going to jump in and get started with the code for our MusicEngine.
Woohoo!
All right, you can see that we currently have the SoundEngine project open.
Yes, we do.
The reason we have this open is since we're going to use the SoundEngine in conjunction with our yet-to-be-coded MusicEngine, we figured it would be a good place to start.
Right, well, it's like that example that we drew up in the intro video, where the MusicEngine is really, you think of it like a time-based event driver, which is going to call on the SoundEngine in order to make some sort of noise.
Now, just for the purposes of anyone who might be viewing and reading words SoundEngine off the screen, we are going to do some quick renaming just to drive home the point that this is the MusicEngine. We're simply using the SoundEngine because it exists.
Yeah, you don't necessarily have to do this. We're just doing it in case you jump into the video and say, hey, they're still doing the SoundEngine. Well,
so
we're not.
Just for the sake of clarity, we're going to change the name of our project from SoundEngine to MusicEngine.
Woohoo.
And we're going to change the name of our solution from SoundEngine to, other side of the words there, MusicEngine.
All right.
Very good. And one last thing we'll do is we'll grab this namespace up here, and we'll simply change this to MusicEngine, and we'll go ahead and irrevocably change our namespace to MusicEngine. And we'll
Living
go ahead
on the edge.
and hit save. And yes, I know in the background our folders still carry the name SoundEngine. But again, if you wanted to separate these, I mean, it would be very easy to rebuild this project from scratch. I mean, it really is just a matter of some assets and these core classes.
Right. So no worries.
But now what we're starting with here, actually, I take that back. Let me go backwards one step, and that is I am going to remove the keyboard input.
Aw. You mean we can't bang on the keyboard and play drums anymore?
Just to keep things clear and concise, just so that we're not looking at any unnecessary code. Yeah. I'm even going to wipe out the default allow you to exit with the back button code.
Wow.
So all we're dealing with here is a bare bone skeleton. So now we have just removed the SoundEngine example from the SoundEngine example.
You got me. Let's
all
go.
right. Now, to get started, the first thing we're going to address is the metronome time calculation functionality of our MusicEngine.
Which is probably the most important key part of our SoundEngine, because really, again, it's just a time-based event driver. That's it.
And to show that, what I'm going to do is let's go down to update. We'll address this first, since update is what we were terming as events in the previous video. So all we're going to do is from inside of update, we're going to call on our SoundEngine and tell it to play track index 2, which if we remember, our zero-based loading of sounds 0, 1, 2, that should be a snare.
Okay.
Now, I'm not going to play right off the bat because knowing how an XNA game functions, we're calling this 60 times a second. And that would sound interesting to say the least if we recall our sample at a rate of 60 hertz.
Oh, I was excited.
So just know that we're sampling every event by simply playing a sound.
So now you want to control the events.
Exactly. Now we want to get into time calculation. Just to show time slowed down, we could do something as simple as this. In our game's constructor, we could take the current game's property of target elapsed time, and we can use this to control the update interval. For example, we could set this to be a new time span with a value of, I don't know, seconds. Let's do 0 hours, 0 minutes, and 1 second. Now, if we run and play our game, well, we can hear.
You've got a 1 second snare drum metronome.
Exactly. So we know that we have indeed slowed down the calls to update down to 1 single second. And this is all well and good for controlling speed, but we need to control this in terms of beats per minute, not seconds. So what we're going to do is establish the conversion necessary to derive a target elapsed time, which is really a time span type, in terms of beats per minute.
Now, as you might recall from the intro, the beats per minute is the first part of our metronome system. That's going to be the part where we actually get one tick, or we'll call them ticks, on every single beat of our rhythm. Now, once we're done with that, we're going to take the duration in between those and we're going to divide them up. That's coming later. I'm just reminding people where we are.
Exactly. That's where we're headed, but we need the initial beats per minute ahead of time in order to get this all kicked off. So what we're going to do is we'll make ourselves a method that will perform the calculation. We'll make a method, void, so we're not going to be returning anything. Set tempo will be the name of our method, and we will take in an integer named beats per minute, or BPM. Finish off the method body. So the idea is to take in beats per minute and kick out a time span representing that tempo. The way we're going to do this is, well, for one, when we run the calculation, we would like this to be performed with as much accuracy as humanly possible.
Okay.
You saw that just a second ago when we're assigning a time span, we have things like hours. Not very accurate.
No.
Minutes, more accurate, but not enough. Even seconds, still not very accurate.
No. Well, 1 beat a second is a really slow song.
Now, we can get all the way down to milliseconds, but there is a core driving force behind the time span that is even more accurate than milliseconds, and that is ticks, that are individual 100 nanosecond spans of time. And just to put that into perspective, a millisecond is composed of 10,000 ticks.
That's pretty accurate.
So, if
Where's the word precise? I think it's precise.
Precise would work.
That's precise.
So, knowing this, why don't we just go for the most accurate measurement when we're setting up our tempo?
The most precise measurement.
Exactly.
All right, I'll shut up now.
All right, over here in set tempo, what we want to do is, well, to begin with, what units are we working with in beats per minute? Well, we're working with minutes, and as far as our unit of time. So the first thing we're going to need to know is exactly how many of these very precise ticks are in a minute.
Okay.
Fortunately, the time span type contains some pre-listed values. One of those happens to be ticks per minute.
Oh, it's too easy.
So very convenient for us. Now, what we actually want to do is use this in conjunction with BPM to figure out exactly what the interval or individual slice of time is going to be. So let's look at ticks per minute. This is actually stored as a type long, so we'll go ahead and store this out in a local variable. So we'll make a variable, type long. Let's call this interval, since this is the interval we're going to calculate. Now, if we just set it to ticks per minute, then that's the amount of ticks in each minute. We want to divide that by the beats per minute to get the number of beats.
Yeah, you'll get the number of ticks in every beat, won't you?
Exactly. So we'll take ticks per minute, divide that by beats per minute, and then that should give us an interval.
Nice.
Now, of course, that is just a variable out here in this function. We need to apply this to the game's target elapsed time. So what we're actually going to do is turn around and say that this dot target elapsed time is equal to a new time span. Now, one of the things that we can feed into a new time span are ticks. So we'll simply feed in our interval directly, since now our interval
contains ticks.
Exactly. So interval has a T in it. That makes it helpful, and there we go. So again, since we're dealing with ticks, we simply apply interval to a time span, and that gives us our new target elapsed time.
All right.
Now down here in game 1, let's replace this line with something that makes sense in terms of musical tempo.
Okay.
So let's run a call on set tempo. But if we wanted the same result, what would we need? If we wanted to have the same 1 second update, what would we need in beats per minute?
60 beats per minute.
Exactly, because then if we had 60 in a minute, divide that by 60, we'd have 1 per second. So we'll set a tempo of 60 beats per minute, run the game, and there we go.
Sounds like it's working.
The exact same result set before, but this time in terms of beats per minute. So we could up this to 120, and so on.
Nice.
All right, this has the core of our timing in place. Now let's factor in the second part of tempo. Once again in the musical discussion, we talked about how in order to actually store notes, at least store them in a sense more accurately than in beats.
Yeah, they need to take place in between beats.
Exactly. So we're going to need to specify just how much space we have, or rather how many subdivisions we have between beats. So we're actually going to extend, or rather enhance, our set tempo method a little bit. We're going to take into account ticks per beat. So we'll take in a second integer called ticks per beat. And now in order to apply this, again, this is a subdivision. So we need to take the number of divisions we would normally get and multiply that, where at 60 beats per minute, we would end up with one interval. If we had a division of 10, we would actually want 10 times as many updates. So we need to take our beats per minute and multiply that by ticks per beat, and now we'll have
a grand total number of updates.
Exactly. So now we can specify that we still want 60 beats per minute, but we actually want to, in accord with our earlier example, run maybe 96 actual updates per beat in order to achieve 4/4 timing with our note set.
Right.
So now we're free to feed in a certain number of ticks in a beat. So let's update our tempo function here.
And again, all this comes down to taking this kind of abstract idea of time as it applies to music and putting it into something that is rigidly quantifiable in terms of the computer.
Exactly. Now, before we jump in here and start hard coding in numbers, we were saying that 96 ticks was equal to a quarter note.
Yes.
So let's actually lock down a few of these note values, if you will.
Probably a good idea.
So we're going to create a set of fields beginning with, let's grab an eighth note.
Okay.
We'll make a field of type integer, and we'll call this eighth note. And we'll set this equal to a value of...
There's an H in eighth.
E-I-G...
Or you got to transpose E-I-G-T-H.
E-I. Like so. And let's see. Yep. And once again, that's going to be half of a quarter note, so a tick value of 48. Of course,
yeah, we decided in our earlier video that a quarter note was going to be 96 ticks. So an eighth note, which is half a quarter note, has got to be 48.
So once again, the quarter note is 96, and one more that might be of interest could be a half note.
Now, you don't necessarily have to put these fields in, do you? I mean, you could just derive it all from math if you knew what a quarter note was, right?
Oh yeah, of course. You could take the quarter note, and by it being a quarter note, you could figure out what a whole note is. You could divide a whole note into any note that you wanted to.
Sure.
Or from the onset, you could just store a whole note to begin with. Part of the reason for being so quarter note centric is just since we were describing this in terms of common time, 4/4 timing, a quarter note is a beat. And that's really the correlation, is that whole, you could say the correspondence between...
Right. That's how they tie together. Common time, 4/4 time, literally calls on a quarter note by name. So it just makes sense to derive all of our timing from the quarter note.
All right, so once again, the half note would be 2 quarter notes, so we'll set that to a tick value of 192. Now, since we're able to specify tick rates, let's actually specify this in terms of 4/4 timing. Let's put down that our beats are going to be 1 quarter note long.
Cool.
Now, of course, we're back to the problem of running this update method many, many times a second.
I was going to say.
So before we jump in here and run, we want to take this new update frequency into account. Before we actually play our note, we're going to do a check. We need to say that only every quarter note's worth of ticks do we really want to play anything. So that means at this point we're going to have to track the passage of time. So what we're going to do is we will jump back up to our fields, and we need one additional field. We'll use an integer called tick to track what the current tick actually is.
Okay.
So back down here in update, we'll say that every time we call update, we will simply increment tick.
Makes sense.
But that gives us our value to check, so now we can run an if statement, say that if our current tick modulus any given note, for example, quarter note, if the result of that division remainder was 0, we divide it evenly into a quarter note, then we'll go ahead and trigger sound playback.
Let me ask you this. If you are using an integer to store your tick, if your game plays for a really long time, is that going to be a problem?
It actually, yes, it does enforce an end limit on how long the game can play. But this amount of time will give you... There was one point in some time past where I had run the calculation on exactly how much time you had.
Yeah.
But it ranged from hours to days.
Yeah, I was just speaking theoretically.
Yes, it does in fact limit the amount of time that you can express going forward.
Right, because then you'd be trying to plug along into an int and you should get a crash.
Exactly, because at some point you'll overflow the int and wrap back around to 0, and to music or to your game that might make it look like time restarted. So yes, it does indeed impose a limit on how long any given song can be. But that's in terms of multiple hours extending to days, and you can actually adjust that number a little bit. If you change what your core tick rate is,
Yeah.
you'll get more or less time in that integer.
I was just curious.
Or if you change tick to be a long instead,
Right.
and store with 64 bits, then you get many, many, many days worth of song playback.
Okay.
So it's all in units that make sense to us. Here in this example where it only has to play for a few minutes, an integer is plenty. For the duration of any single song that our game may want to play, an integer is still plenty.
Cool.
Alright, so now that we're tracking the passage of time, I am going to do one small thing, and that is to take into account the fact that direct sound takes some time to initialize and get everything ready for playback. What I'm actually going to do is delay for a full second before we actually start calculating time, and we'll do this with another simple if statement where we check our current game time dot total game time and look at the total seconds that have passed. And if we're greater than 1 second, then we'll go ahead and begin playback. Again, just giving some time so that direct sound can fully initialize.
Right.
Now, we should be ready to run. We've greatly increased our update frequency based on some timing constraints, and then set ourselves to look for quarter note intervals out of that overall update range and play sounds. So now if we play, we have a nice fast update rate.
Yep.
And again, this is in terms of 120
Yeah, it sounded
beats
like
per minute.
120 to me.
So the question is, now that we've gone around the world to get the same result, what can we do with our newfound power? Well, if we start using different notes and mixing in different drums, we have the basis for creating sets of rhythm.
Yeah.
So let's throw the hi-hat into the mix. Let's make another if statement.
You basically got procedural drum playing.
Exactly. That's a very good word for it. So if we take our tick value and we modulus against, say, an eighth note,
Yeah.
and if that result divides evenly, let's take our sound engine and play sound index 1, or just for visual reference, a hi-hat.
Cool.
And then we're still playing the drum on the quarter note, or excuse me, the snare on the quarter note, so we should play the snare, 1 snare to 2 hi-hat hits. So let's go ahead and run and play. And we do, very nice.
Yep, sounds good.
So of course we could separate this out a little bit more and say that maybe once every half note, and play the snare.
Oh, I know a song that starts this way too.
And then we could even go so far as to take our tick offset and actually offset where this occurs. Actually, let me do this first to explain why we might want to offset. Let's have a little bit of fun, and let's throw a new drum in place. I don't think we were yet loading the kick in our previous example. There's no reason we couldn't. Let's actually take and duplicate one of the lines where we're loading sounds. And let's say that as the last sound that we load in the kick drum. So that should be track 0, 1, 2, track 3 should be our kick.
Nice.
So let's copy one of these ever so handy code snippets that allow us to identify and play given tick intervals. And let's say that, once again, every half note, we play the kick. And I see some spelling, so being lazy as I am, we'll just copy and paste and patch that right up. So naturally, this is going to play the kick and the snare at the same time, which playing over each other makes it sound almost the same. But let's now offset our snare. Let's move it, I don't know, maybe a quarter note ahead of the kick. So let's say if tick plus quarter note.
Oh, you're just having fun now. Hey, yeah.
So now,
Get into that.
and now if we went further and started doubling up the kick, then we can get more and more complex rhythms in place.
Very nice.
But again, this is now showing that we have not only given ourselves the basis of musical tempo by which to drive our game, we can now subdivide that and give ourselves enough resolution to compose rhythms.
Well, we've got time and we've got notes. Is there anything else you'd like to add right now?
For this lesson, I think that's it. We've got the core of our music engine in place, and from here we'll look at some more advanced topics such as storage.
Very cool. So that's going to wrap things up for this video. Thanks a lot.